So for constant volume systems, the heat capacity is going to be equal to the derivative of the internal energy with respect to temperature. Let's now consider the case where we have a constant pressure system. So the constant pressure heat capacity otherwise known as the isobaric heat capacity. In this case, we're going to once again consider a piston cylinder system. But now, rather than our piston being locked into place so that it doesn't move, we're now going to allow the piston to move, but on top of the piston, we're going to put, some sort of weight. So that, if you remember from all our force balance examples, this would mean that the pressure on the piston, there's some sort of force acting down on it. So this is going to maintain a constant pressure for our system, right? So constant P, because it's controlled by the force balance now. To this system, we're going to add some heat. And because the pressure is constant now, that means when we add this heat, our temperature and volume are going to change. All right, the system can expand in order to accommodate, the higher temperature of the system, even though that the pressure is constant. Once again, let's evaluate the energy balance for this situation. We have delta U plus delta EK plus delta, that should be K, plus delta EP is equal to Q plus W. All right. Let's now simplify the terms in the energy balance. There's no acceleration, and there's no change in height or change in a potential field. So those are 0. We're going to keep Q. We're going to keep the internal energy because the system is changing temperature. As far as the work, though, as I mentioned, as the heat is added, the system can change volume, right? So we do have a work term. And what I'm going to do is I'm going to rewrite this work term in terms of its boundary work, or the pressure and the volume, all right? So the work is going to be equal to the change going from the initial pressure and volume to the final. And we have to remember the order here. Because I'm on the right-hand side, where I'm dealing with the Q plus W terms, I'm going to write the initial first, and then the final. Right? Well, on the left-hand side here, all this stuff is final minus initial. Because I'm on the right-hand side, everything is flipped, right? So now I'm looking at initial minus final. So I'm just pointing that out because that's a subtle detail, but it's a very important one. And that's because in the next step, I'm going to move those PV terms to the other side. So that now what I have is PV final minus PV initial and because the pressure is constant, right, we're in a constant pressure system, I'm going to pull that out plus P, and so what I'm left with is V final minus V initial, and the shorthand for that is a delta, right? Final minus initial, P delta V. That's equal to Q. Now, of course, U plus P delta V, all that is delta H. So in the end, what I have is delta H is equal to Q If I divide both sides by the mass, I have specific enthalpy is equal to the specific heat. And so, if I now go back to the definition of the heat capacity, and I'm going to put a subscript P because now we're at constant pressure. Or specific heat over delta T, the specific heat term can be replaced with the enthalpy, specific enthalpy. And if we go full force with our definition, that means our Cp is equal to the partial derivative of the enthalpy with respect to temperature at a constant pressure. If you plotted your specific enthalpy versus temperature, that slope would be the heat capacity for a constant pressure system.